Okay. Go ahead and get started. We are going to do section 4 or 5 today, which is working a little more with matrices. So we're going to recap, kind of review the fact of what's called the identity matrix. We have talked about it before. So the identity matrix is also recognized as capital letter I. And what we have is ones along the principal diagonal, meaning from upper left to lower right, and zeros everywhere else. So the 2 by 2 identity looks like that, 1, 0, 0, 1. I could make a 3 by 3 identity, 1, 0, 0, 0, 1, 0, 0, 0, 1. So the ones are always along that principal diagonal from upper left to lower right, and there will be zeros everywhere else. Okay, so when we have a square matrix, we can multiply by the identity. And what's going to happen is following. I take any identity times its corresponding square matrix, or I do it the other order, the square matrix times its identity. It's not going to change the results. It's still going to stay exactly the same. So I'll write an example out here for you. I take 1, 0, 0, 1 and multiply it by the matrix 2, negative 3, 5, 7. Remember, we did the multiplication last week, so we took like the top row, first row to get first row times first column to get the first row, first column value. So you're taking 1 times 2, 0 times 5. It's just giving me 1 times 2. So what happens is this doesn't change. So when you multiply any matrix by the identity, the matrix stays exactly as it is. See a few people still writing, so I'll give you another minute there. Apparently that's supposed to actually go on the next page, so I apologize. It follows the fact of if you take any number times 1, it doesn't change. So the regular property identity rule for multiplication, I could take 5 times 1, it's still 5. I could take 22 times 1, it's still 22. So it's the same rule that's happening here. So The multiplication rule is 1 times any number keeps it that number. So we can expand it to matrices, and it's the identity times the matrix keeps it the matrix. So that was actually supposed to go on this slide here, but we made it work. All right, I'm going to expand it to this one here. Now, you can see that these are not square matrix times a square matrix. Square matrix means it's the same rows, same columns. But if I look, 3 rows by 3 columns, this is 3 rows by 2 columns. So as long as that middle part matches, yeah. The 2 in the middle have to be the same in order to be able to do the math. The 2 on the outside are what give you your final dimensions. Yeah, so the middle here has to be the same. And then the end values mean that in the end, this is going to be a 3 by 2 when I type this. So 3 rows, 2 columns. Other thing is you notice that this is, okay, identity times matrix. I'm going to be able to do this. So it actually doesn't change the result here. Okay. When we work with numbers or matrices, we also have what are called inverses. So an inverse is something that undoes itself, right? So when we talk about like an additive inverse, just talking basic numbers, we're talking about addition properties. So if I just look at numbers and addition, so what's the identity in addition? So let me go over here. So addition. The identity means that if I add it to a number, it doesn't change the result. So what is the addition identity? What number can I add to any number that doesn't change my result? Yes. Right? So if I take 5 plus 0, it stays 5. So 0 is the addition identity, meaning that if I want to find the addition inverse, my goal is take a number, what do I add to it so that it makes the addition identity? What would I have to add to this number to make it turn into 0? -5. Okay, so additive inverses are, you have a number, you add its opposite, and you make 0. That's because any number plus 0 equals the number. So just talking about, I want to talk about addition identity to then go into multiplication identity and inverse. So multiplication, working with multiplication, its identity is 1, because when you multiply number by 1, it doesn't change the result. So multiplication identity equals 1. So when we're working with multiplication, let's say our number is 3, your goal is to determine what you multiply by to get the identity of 1. So what would you have to multiply 3 by in order to turn it into 1? There's a 3 involved in it. 1/3. So if I have a number and I multiply by its inverse, I should get 1. That is the multiplicative inverse. Okay, so inverse just means you do something to what you are given to make it equal the identity. I can do that with addition. I can take a number, I can add its inverse and create the identity. Multiplication, I can take a number, multiply by its inverse, aka reciprocal, and get the multiplication identity. So the same thing is going to happen when we work with matrices. If I take a matrix, times it by its inverse, and the way we're going to write inverse is m to the negative 1 power, I should end up with the identity matrix of 1, 0, 0, 1, or 1, 0, 0, 0, 1, 0, 0, 0, 1. So with any matrix, I could add numbers, add all the opposites to get a matrix of all zeros. I can take a matrix and multiply by its inverse, and I should create the identity matrix. So here's an example. On the next slide here. So is the matrix 2, -3, 1, -1, 2, sorry, is it the multiplicative inverse of 2, 3, 1, 2? So the goal of this question is saying, if I take matrix 1 times it by matrix 2, do I get the identity? Bless you. 2, -3, -1, 2, multiply with 2, 3, 1, 2. So we're going to review what we did last week. So row 1 times column 1 is going to give me this upper left value here. So 2 times 2, it's 4. -3 times 1 is -3. 4 minus 3 is 1. So if you need to see it out, it was 2 times 2 minus 3 times 1 was 4 minus 3 was 1. Okay, next one is row 1, column 2 is what I want. So row 1, column 2. So 2 times 3 minus 3 times 2. That's 6 minus 6, or 0. So that's going to go in that spot there. So far, so good. We are getting close to the identity matrix. Okay, next spot down here. This is row 2, column 1. So I'm going to take a row 2 times column 1. So -1 times 2 plus 2 times 1. That's -2 plus 2, or 0. So that's correct. And then this spot here is row 2, column 2. So row 2, column 2. -1 times 3 plus 2 times 2. That's -3 plus 4, or 1. So are these, in fact, inverse matrices? Yes, because we got the identity. Okay, so now we need to figure, still going, are these inverses? Okay, and then I think I talk about how we actually find it. That should be A and B. All right, so 2, 2, -1, -1, and 1, 1, -1, -1. So what we want to do is we want to multiply these and see if we do, in fact, get our identity. If at any point, if I do the first value and it's not a 1, I can stop because I know it's not going to work, right? If I do the second value and it's not a 0, I can stop. So you either keep going until you get the identity matrix or you stop as soon as something doesn't match up. All right, so if we take first row, first column, 2 times 1 plus 2 times -1. That's 2 minus 2, that's 0. So I can already stop because that doesn't work, right? So stop, no, doesn't work. Okay, so let's look at the next one. I'm just going to turn this into a big multiplication here so I don't have to rewrite them. All right. So let's see. Row 1, column 1. Okay, 1 times 3 is 3. -1 times -2 is 2. And 1 times -4 is -4. So 5 minus 4, 1. That's good. All right, I'm going to keep going. I'm going to take that first row now times the second column. So let's see. 1 times 3 is 3. -1 times -2 is 2. 1 times -5 is -5. 5 minus 5, 0. So that's good. And then first row, third column. 1 times -1, -1. -1 times 1 is -1. And 1 times 2 is 2. So -1 plus -1 plus 2 gives me 0. All right, first row done. All right, so next up, we're going to work second row with all 3 columns. So let's take that row, first column. 3 times 0 is 0. 2 times -2 is -4. -1 times -4 is +4, gives me 0 when I add them together. Okay, we'll take that row times the second column now. 0 times 3 is 0. 2 times -2 is -4. And -1 times -5 is 5. -4 plus 5 is 1. This is looking promising so far. Next one here. Let's go purple. All right. 0 times -1 is 0. 2 times 1 is 2. -1 times 2 is -2. Add them all together, 0. 3 more. Should be 0, 0, 1. All right. So 2, 3, 0 times 3, -2, -4. 2 times 3 is 6. 3 times -2 is -6. 0 times -4 is 0. That makes 0 when I add. 2, 3, 1 times the middle column. 6, -6, and 0. Make 0. Last one. That one times that one. 2 times -1 is -2. 3 times 1 is 3. 0 times 2 is 0. -2 plus 3 is 1. Yes, we have an inverse. Okay. So, how do we actually find an inverse if we're just given our first matrix? Well, what we're going to do first is you're going to set up an augmented matrix. I did not spell that right. Let's try that again. Augment your given matrix with your identity matrix. So I'm going to take 2, -6, 1, -2. Augment it just means you're going to put that vertical line and then put the identity on the other side. Okay, so we are going to do the first one by hand. So step 2 is we're going to do our row operations like we did back in the beginning of matrices to get the left-hand side to be your identity. So what we're going to do is we're going to do the work so that the left side becomes the 1, 0, 0, 1. So make L equal identity, make left equal identity. That's what my little abbreviations mean. All right, so the first thing I need is I need that 1 in the upper left-hand spot. So what I can do is I can take the entire first row and divide by 2, and that'll turn my 2 into a 1. So row 1, divide by 2, replace it in row 1. So 2 divided by 2 is 1. -6 divided by 2 is -3. 1 divided by 2 is a half. And 0 divided by anything is still 0. That does not change. And I did not touch the bottom row. Okay, once you get a 1, your goal is to get the 0 below it. Well, I have 1 and 1. So all I actually need to do is subtract these 2 rows. It's already set up. So what I can do is I can take row 1 minus row 2. No, I'm going to do the other way. Row 2 minus row 1. Row 2 minus row 1, replace row 2. So I'm not touching the top row, so I'm going to leave those in red to show I didn't touch them. And I'm changing everything in the bottom. So I'm going to take row 2 minus row 1. So 1 minus 1 is 0. -2 minus -3 makes -2 plus 3, or 1. And look at that, my next step's already done. 0 minus a half is a -half. And 1 minus 0 is 1. So it's always 1, then 0, then 1, which we already have. So we just need to get our 0 up here. So the last step is we're going to multiply row 2 by the opposite of -3. So this is where we're working with that additive inverse, right? The additive inverse, the goal is to get that 0 there. So this is what we do back here when I was talking about addition identity. The opposite of -3 is +3 because my goal is to make it a 0. So we're using these identities all through this process. So I'm going to multiply by +3 so that if I add it to row 1, it cancels out the -3. I keep my green on the bottom because I'm not touching the bottom. And this is actually staying the same. So let's see, if I take this value, 1, times it by 3, that's 3. 3 plus -3 is, in fact, 0. We've done the additive inverse. Okay, next one, if I take -1/2 times 3, so -1/2 times 3 is -3/2. And then I want to add a half to that. Leaves me with -2/2 or -1. And then 1 times 3 is 3. 3 plus 0 is 3. So that means this over here is now M inverse of the initial matrix. So if I were to take this times this, I would get the identity matrix. All right. So I'm going to, hold on, I want to look at, why do I not have, okay, so I will come back to this problem in a minute. I do want to show you that if you were working by hand, or 2, -4, -3, 6. Okay, if I were to work with this one, and we're not going to do the whole process because I'm going to show you something that happens. So I start with this 1, 0, 0, 1, and I augment it with the identity. So first thing I need to do is get that 1 in this upper left position. So I'm going to start with taking row 1 and divide everything by 2. I'm going to replace row 1. So 2 divided by 2 is 1. -4 divided by 2 is -2. 1 divided by 2 is 1/2. 0. Thank you. 0 divided by 2 is 0. And then I'm going to leave that bottom row as is. So I'm looking for the additive inverse of -3. That is going to be +3 because -3 plus 3 makes 0. So if I take row 1 times 3 and add it to row 2, I'm going to replace row 2. So top row is going to stay as is. Then we work at this. 1 times 3 is 3. 3 plus -3, 0. That's great. -2 times 3 is -6. Plus 6 is 0. 1/2 times 3 is 3/2. 0 times 3 is 3. 3 plus 1. Sorry, 0 times 3 is 0. Plus 1 is 1. However, this is a problem. Okay? We cannot have zeros equaling numbers. Right? So this doesn't work. Now, the reason why is because if you look here, this second row is exactly -3 times the first row. One row is an exact multiple of the other, so you cannot have an inverse. What's going to happen is that entire row is going to cancel out, which you see here, makes a bunch of zeros, so it does not, in the end, have an inverse. So just like when we were solving them, if we got 0, 0 equals a number, we said we can't do that. It doesn't have a solution. It's no way to make 0x plus 0y's equals 3/2 and 1. You can't do that. All right. So how would I do this in Desmos if I wanted to do this here? So let me get my Desmos open. And I want, under math tools, I want the matrix calculator. Okay, so what you're going to do is you're just going to enter your matrix. 2, -6, 1, and -2. And then you can see on the bottom here, we've worked with the RREF button. We've worked with the squared button. You can see here, there is also an inverse button. That's the -1 power, a to the -1. So I want to find the inverse of matrix A. So I'm going to hit A and then hit that -1 button, which is the inverse button. Now, when you create inverses, it's very common to get fractions. So I love the Desmos calculator because it will convert any of these two fractions for you so that you can get the exact answer and not just a decimal. Right? So there is an inverse. Okay, how do I know that those are inverses? Well, if I took that first matrix and I multiply it by the second matrix, I should get the identity. And I'm going to show you that part in just a second. Okay, so if I go back where it said, are these inverses? So 2, 2, -1, -1, and 1, 1, -1, -1. So the quick way to check if they're inverses is just multiply them. Is B times C the identity? Is that the identity? No. Okay, so that one didn't work. And we realized that here, we said we got a 0 in this upper spot. So we said, no, it doesn't work. So if I want to check inverses here, for this guy, could I turn this into a 3 by 3? 1, -1, 1, 0, 2, -1, 2, 3, 0. 3, 3, -1. Whoopsies. -1 there. -2, -2, 1, -4, -5, and 2. All right, so I can check. B times E gave me the identity. All right. So we want to find the inverse of 2, 1, 4, 3. So I'm going to enter my new matrix. 2, 1, 4, 3. I'm on matrix F, so I'm going to hit F, and I'm going to hit inverse. And I will always convert those into fractions. So this one is inverse is 3/2, -1/2, -2, and 1. So I showed you the initial ones by hand to practice the multiplication, to practice some row operations, but I'm also showing you here. Right, let's do our next one. Here is a 3/3. -5. Oh, nope, nope, nope. -2, -2, 2, 1, 0. No. 1, 0, 1. Okay, I'm on matrix G now, so I'm going to do G inverse. Gives me an answer, right? So this is the inverse of G. So 1, 2, 2, -2, -3, -4. -1, -2, -1 is what it was. Get out of here. All right. Last one here. 2, 1, 1, 1, 0, -1, -1, 0. I'm on matrix H. So H inverse. And it gives me this error. It says singular matrices do not have an inverse. So if I look at this, what do you notice about these two rows? Right? This one is an exact multiple of the other one. If I took row 2 and times by -1, what row did I make? That's row 3. So this row is an exact multiple of the bottom row, which means this bottom row completely cancels out, no inverse. Okay, so that's why I showed you the one by hand first to understand what is actually happening when you go here and it's saying there isn't an inverse. Because if I just said there's not an inverse, you're gonna be like, but why? Why isn't there inverse? Every other one we've got had an inverse. So if you ever have a row that's a multiple of the other, it will not be able to make an inverse. All right, so all of this, why do we use inverse matrices? What is the purpose of them? Well, one of the practical applications for inverse matrices is a process called cryptography. Has anybody ever heard of that before? It's taking a message and coding it so that along the process to whoever you're trying to get your message to, anybody else that sees it cannot read that message. Okay? So what happens is there's an original message you have that you use a coding matrix to turn it into a bunch of different other symbols or different letters. You then send the coded version to a person. You give them the key to decode it, and then they can convert it back into your original message. So the way that this works is it says the following message was encoded using matrix B. So each number represents either a letter or a space. So 85 is the first letter, 74 is the next one, then 27, 109, 31, all the way through. So what we need to do is we need to create a matrix out of my initial string of numbers. Now the question becomes, though, how do I know how big to make this matrix? Well, it's based on your encoding matrix. You take the number of rows in your encoding matrix, and that's how many rows will be in your initial matrix. You may have multiple extra columns, and that's okay. Now, the way you do this is we're going to read across the string of numbers and fill in a column. Once I get to the end of the column for values, I'm going to go to the next column and start over. So 85, 74, 27, and 109. Again, I'm doing 4 rows because my encoding matrix here has 4 rows. And then I'm going to start over. 31, 27, 13, 40. 139, 73, 58, 154. 61, 70, 18, 93. 69, 59, 23, 87, 18, 13, 9, and 22. Now, if there was a case where the last number was 9 and there was no 22, you would just put in a 0. You have to finish the matrix. You would just fill in zeros for what's left in that last column. Okay, so this is my initial matrix. This is my encoding matrix. So in order to decode it, I have to take my encoded matrix times the inverse of the coded matrix. So it says take the code matrix, that's this guy here, code matrix, times it by the encoder's inverse. Now, this is also why we use technology, because I would never, ever, ever expect you to do this by hand. I have maxed out my matrices, so I got to start over here. New matrix. So this is, it's 4 rows, and it was 1, 2, 3, 4, 5, 6 columns. Okay. 85, 31, 1, 39, 61, 69, 18. Next row, 74, 27, 73, 70, 59, 13. 27, 13, 58, 18, 23, and 9. 109, 40, 154, 93, 87, and 22. Okay, I'm going to enter my matrix B as a 4 by 4. 2, 2, 1, 3. 1, 2, 2, 1. 1, 1, 0, 1. 2, 3, 2, 3. Okay, so it says take your code matrix, so that's matrix A, times B's inverse. So B inverse. I did it. backwards. Hold on. B inverse times code matrix. Because I have to have the columns and rows in the correct order. This is 4 by 4. This is 4 by 6. Head backwards. And clearly, if you do it and it gives you the error, it knows you did it backwards. So B inverse times A. Now it works. And you're probably like, but how? What does this even mean? I'll show you on the next slide. All right, so we are going to use this guy here. This is an alpha numeric code. A is the first letter of the alphabet, B is the second letter of the alphabet, so on and so forth. And remember, the way we entered this in was down, 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 all the way there. Okay, so the 18th letter of the alphabet is R. So that's the first letter. R. 1 is A. 23 is W. 8 is H. 9 is I. 5 is D. Did I type something wrong? What did I, hold on. R-A-W-H-I-D-E. There it is. I skipped. Yeah. R-A-W-H-I-D-E. 0 stands for space. So rawhide is the first word. A 0 represents a space. 20 and 15, that's T and O. So 2 and then a space. That guy back up for you. So 23, W, 1 is A, 12 is L, 20 is T, W-A-L-T, E, R, Walter. Then there's a space. Walter. Look at the last one here. 18 is R. E-E-D, end. Rawhide to Walter Reed. It's a military phrase of some sort. Yeah. You figure out what it's going to be first. So like, if I just wanted to say hello, okay? H is 8. E is 5. L is 12, right? A, B, C, D, E, F, G, H, I, J, K, L. L. So 15. So there's my hello, right? What I'm going to do is I'm going to pick a random matrix that I'll be able to inverse. So let's see, it's got to be 2, because this is 2 by, hold on. This is 2 by 3. I'm going to multiply it by, I'm going to put it in front. B times this. So let's see if I can do this right. 2, 3, 1, 5. I've never actually done one, so we're gonna see if it works here nicely or not. I said 2, 3, 1, 5. Okay, so my 2, 1, 5. Dang it. Okay, my matrix. It's an extra column. 8, 12, 15, 5, 12. What is going on? So if I took C times D, that is what I would send you. Okay? And I would send you my initial matrix C. So you would then take, hold on, I got to enter this as a new matrix here so that I can have it 31, 60, 30, 33, 72, 15. So you take C inverse times what I sent you, and it gave you back what I originally had as hello. Cool. All right, so this is your guys's problems to try for today. I'm gonna make an upload spot, so if you want to upload them, you can. When you are working in, so let me make it quick and then I can show you how, because you can actually use the editor. There's a math editor in Blackboard. So like if you have an inverse, you wanted to type a matrix, you could actually do that. Okay, so this will be in the week 4 folder. And when you go in to do it, I gotta make sure I'm in student mode or else it won't let me show you as a student how to do that. Instructions. Okay. So when I'm inside here, and you're in your little text box doohickey down here, if you hit this plus button, there's a math editor. So I can then go in here and it's going to pull up a whole bunch of math stuff that I could do. So here's fractions, square roots. Well, matrices are over here and you can see. So like if I need a 3 by 3 matrix, I can literally click that. It's going to make a 3 by 3 matrix. If I want a 2 by 2 matrix, I click this. I can actually make it any size, 2 by 2, 3 by 3, and it's going to set up the matrix. And then all I have to do is type in my numbers. And if I had a fraction, like I could go back here and say that's 1/2 and enter a fraction. I'm just going to put random numbers. Oops. So then when I hit insert, it's going to put it right there for me. So then you would just go back to the beginning and say like, oh, this is problem number 19's answer, whatever. Or you can do it by hand like you've done it before. Doesn't matter. I don't care. I don't want to actually do that, but that is all there for you. You have your letter code there. So yes or no, find inverses, and then decode.